Hello, everyone. Welcome to the TEAS Math Section workshop presented to you by the ARC. We are just going to go over some basic math that you want to know for the test, as well as the question breakdown and time allotted for each. So the math section is approximately 23% of the entire exam. An overview of the topics covered on this portion. First is just some basic math from MDE 10. They'll go over fractions, how to add, multiply them, working with mixed numbers, and converting fractions to decimal and vice versa. Then are some place values, so tenths, hundredths, etc. This might be rounding to those decimal places or maybe just identifying those place values. Next, we'll go over area, perimeter, and volume, using those as equations for rectangles, squares, circles, that sort of thing. Then PEMDAS, parentheses, exponents, multiplication, division, addition, and subtraction, using that order of operations to solve equations. And next, working with percents. Right, the next math section is algebra, which I know can be pretty taxing on some folks, but we will go over it. So first, there's rates, then inequalities, solving inequalities, and then FOIL method. So first, outer, inner, last, when multiplying out polynomials. Then is some graphs, types of graphs, and how to read them. You'll have to work with maybe their equations or just reading and interpreting them in general. Ready? So an overview of the questions in the math section, there's 38 of them, and you have 57 minutes to complete it. That's an average of 1.5 minutes per question, which might not seem like a lot, but don't worry yet because some will be quicker. You might not have as much knowledge on some of them, so they'll take you longer, but others of them will go a lot faster. So the time balances out as long as you manage your time properly. And this is a breakdown of the questions. So 16 questions are pulled from the algebra and word problems set, which I know might not be everyone's favorite. So make sure you look over word problems. Make sure that you're comfortable pulling out pieces of information from that and what's important versus what's not. And then 18 questions are from the measurements and data section. So that might be like conversions or graphs, that sort of thing. Ready. So we'll just go over some basic math from that first section now. So order of operations, as I stated at the beginning, this is parentheses, exponents, multiplication, division, addition, and subtraction. You need to know what steps to take for any problem. So this might be in algebra cases or just any order of operations problem in general. This is the order that you solve those problems in, and you carry out these operations in this order. So if you need an acronym to remember the order, please excuse my dear Aunt Sally is a really good one. It's helped me personally remember this very, very well. Alrighty. Next is unit conversions. So you must know how to convert units via dimensional analysis. There's an example over here in the right graphic. So the first step to any problem like this is write the two givens, what you're starting with and what you're ending with. So below what's in purple, we have 24 kilometers per minute. All right, that came from the problem that's in purple. It says convert 24 kilometers per minute to meters per second. Our first given is that 24 kilometers per minute, and we need to get to meters per second. So we put that on the right-hand side so that when we go to cancel out later on, we know what we need to end up with. The second step is fill the middle with conversion factors. That's what's given in blue at the bottom. So we know that we have to make it to meters per second, but we start with kilometers per minute. Therefore, we have to cancel out kilometers and minutes. How we do this is they started with kilometers in this case, right? We have to get to meters. So we know that 1,000 meters is equal to 1 kilometer. Kilometers goes on the bottom because kilometers was on the top originally. So those cancel out, those units. And then we're left with meters at the end. And then we also have to cancel out minutes. Well, we have to get to seconds. So we know that 60 seconds is equal to 1 minute. And since minutes was on the bottom in the first red fraction, we put minutes on the top in the last fraction and 60 seconds on the bottom. Now, whatever numbers are next to each other in the top, we multiply, and whatever numbers are in the bottom, we divide by. So in this case, we'd multiply 24 times 1,000 and then divide by 60, and that gives us our 400 meters per second. So that's how you solve dimensional analysis problems. Ready. Next is working with place values. You must know what value something has at a specific place. To move the decimal back, you multiply by 10. To move the decimal forward, you divide by 10. All right? So, starting over all the way to the right with the 7, that's the 10,000ths place. It's the smallest place value in this case. Then we move to the left. That's thousandths. Then we move to the left again. That's hundredths. Then we move to the left again. That's our tenths place. Then we have our decimal point, which means that everything to the right of it is less than 1. Ready? To the left of the decimal place, we have our ones place where the 5 is. Then to the left of that, we have our tens place where the 6 is. Then to the left with the 3, we have our hundreds place. Then to the left of that comma is our thousandths place. Then to the left of that, we have our 10,000s place. To the left of that, where the 3 is, we have our 100,000s place. And to the left of that, we have our millions place. Ready. So next is conversions. So we must know how to convert fractions into decimals. You do this by dividing the numerator by the denominator. All right. So for example, if we had a fraction that was 1.00 divided by 4, our numerator being 1.00, fraction bar, and then our denominator being 4, this is how we would solve this, all right? So you'd put the 1.00 on the inside of the division bar, and then on the outside we put the 4, which was the denominator. Our first step in a problem like this is looking and seeing if the 4, what's on the outside, goes into the first number, right? We know that 4 does not go into 1. So we put a 0 above that 1, right? Now, we can put that decimal place right above where the 1 below it is, because we know that that's where the decimal has to stay. We also can move now to looking in 4 goes into 10. Once you figure out the first place, you add a number after it and see if the outside number goes into that. So now, does 4 go into 10? It does. So we put a 2, because 4 goes into 10 2 times, above that 0 that we just used. Then we multiply 2 times 4, which is 8. We put that under that value that we just used, the 0. And then we subtract. 10 minus 8 is 2. All right? Now we bring down the next 0. And now we have 20. Well, 4 goes into 20 5 times, so we put a 5 on the top above that 0. And we multiply 5 times 4, which is 20. So we put that below the other 20, and then we subtract. 20 minus 20 is 0. So we have a remainder of 0. So what is given is the answer at the top. 1.00 divided by 4 is 0.25, and that is how you will solve problems like that using long division. Right, next is conversions. So you must know how to change a decimal into a fraction. You need to first know the place value of the last digit, then put that number over that place value. All right, so over on the right in the image, if we start with the first one, we have 0.3. It's written backwards, but we can start with the decimal first. 0.3, right? That 3 is after the decimal, and it's in the first place after the decimal, which is the tenths place. So we can put that 3 over a 10, and that's how you get your fraction, because it's in the tenths place. Same for the next one, to the right of that. The 7 is in the tenths place after the decimal, so you put 7 over 10, and that's your fraction, 7 tenths. And that's the exact same for the one to the right of that. Then on the next line, 0.11, those two ones The first one's in the tenths place, the next one is in the 100th place. So we know that the rightmost decimal place is the 100th place. So we put 11 over 100. So 11 hundredths. And that is our fraction. Then to the right of that, same thing. We know that our smallest decimal place is the 100th place. So we just put that 23 over 100. And then the exact same thing for the one to the right of that. That turns into 7 hundredths. And it's okay if a 0 is in the tenths place, right? All that means is that 7 out of 100, not 70, not 17, right? It's just 7 over 100. And then the bottom line here, we have 0.567, right? The last decimal place where the 7 is the 1,000ths place. So we can put 567 over 1,000. 567 thousandths is how you would read that fraction. Then same thing for the next fraction, right? It started off as 0.037, right? So we put 37 over 1,000 because that 7 is in the thousandths place in the decimal. And same thing for the one to the right of that, 0.008. That 8 is in the 1,000ths place. So we put 8 over 1,000. Now, if you need to reduce these fractions in any way, which you would have to reduce the last one here, the 8 thousandths, you can. And you would probably have to put your answer in the reduced form. But this is just showing how you directly convert the decimal to the fraction. Ready? Next, we're going to be going over area and perimeter. So first, perimeter is the total length around a shape, right? You can see in the left picture, perimeter represents the fence, right? It has nothing to do with what's on the inside. It's just going around it. And I think of it as a fence. That's how I remember perimeter versus area. Perimeter is more the fence, area is what's on the inside. So for squares, our perimeter equation is perimeter equals 2 times our length plus 2 times our width. So we would just take our length multiplied by 2 and add 2 multiplied by our width, and we get our perimeter. You can also just add up the 4 sides of the squares. That works as well. For a circle, our perimeter is known as circumference. Circumference is the perimeter of a circle. And that equation is circumference equals 2 times pi, in this case you would use 3.14, times the radius of the circle. The radius is the line from the center point out to the side. It's just half of the diameter, right? Now, area is the amount of space covered by a shape. So in the left, the grass is the area of the square, right? The units are squared, such as centimeters squared, meters squared, that sort of thing. For squares, our area equation is area equals length times width. So if you had a square that was 3 centimeters by 3 centimeters, you would multiply 3 times 3, and your area would be 9 centimeters squared, right? For triangles, the area equation is area equals 1/2 times its base times the height. A lot of times you'll see this as you'll have a triangle and it'll be sitting on a, flat. The bottom will be the flat portion. Sometimes it'll be turned, other times it won't. But then there might be a dotted line down the middle of the triangle, and that represents your height. And there should be numbers in both places. So let's say our base was 1 centimeter. Our height was 2 centimeters. All right. We would do 1/2 times 1 times 2. All right. So that would give us 1/2 times 2 times 1 is 2. So 1/2 times 2 is just 2 over 2, which is equal to 1. So 1 centimeter squared would be the area of that triangle. Ready? Next is for circles. The area of a circle equation is area equals pi, 3.14, times the radius squared. You square that radius first and then multiply by pi, by 3.14. That is an order of operations problem right there. Same for the first one with perimeter, the squares. For squares, perimeter equals 2 times length plus 2 times width. You multiply 2 times the length first, and then you multiply 2 times the width, and then you add them together. Do not add first. Be pretty difficult to add first in that case, but make sure you are using PEMDAS when you are solving these equations. In addition, for pi, you can also do 22 divided by 7 or 22 sevenths. Sometimes it's just easier to type 3.14 into the calculator. Alrighty, next is working with percents. So percents tell you how much relative to 100% a given number is. To find the percent of a whole number, multiply the whole number, the percent in decimal form. To convert decimals to percents, multiply by 100. To convert percent to decimal, divide by 100. Righty, so in this picture to the right, we have an example. It says, what percentage is 24 out of 200? All right, so you always want to put the is over the of, right? So in this case, we would put 24 over 200, all right? So when we put 24 over 200, we get 0.12, and then we can multiply that by 100 to get 12%, right? Because when we put 24 over 200, we get a decimal, but we're still not done, right? We still have to multiply by 100 because that's how you convert a decimal to a percent, right? So you can think of it as part over whole equals its percent over 100. Or you can think of it as part over whole, so 24 over 200 times 100 equals the percent. You can also think of it as percent times the whole divided by 100 equals the part, depending upon what you are looking for in this equation. If you were trying to get to the 24, you weren't given that number, you would use the last equation at the bottom to solve for that number, right? If you were given 12% and the 200, you would put 12% times 200 divided by 100, and you would get 24. Ready? So next we'll be going over some algebra sections for the test. Ready? So first is solving for x. So this can be any variable. Sometimes it'll be y, might be z, p, whatever it is, just an unknown variable in general. We need to know how to solve for the unknown variable. We need to try to get the variables by itself, work from the outside towards the inside. Remember PEMDAS, always remember PEMDAS in every problem that you do. Sometimes it might, not be relevant, but you always want to keep it in the back of your mind for when it is relevant. Also, remember to add or subtract like terms and check yourself by plugging in the answer that you get back into the variable, right? We'll go over this on the right. So in this equation on the right, we are given 2 parentheses times x plus 5, then minus 7 equals 3 times x minus 2. All right, so first we need to start off by distributing the numbers outside of the parentheses that are being multiplied by the things in parentheses to kind of expand the problem a bit. So first, the 2 times x plus 5, we're going to multiply the 2 times the x. Underneath that, we get 2x, right? Because we can't multiply those numbers out fully. X is not a number, it's just a variable. Then we multiply 2 times 5, which gives us 10 below. And then we just have minus 7 at the end of that. Just tag it on to the end because it's not being multiplied by the 2 or anything else. It's being subtracted after the others, right? Then on the right-hand side of the equation, we multiply 3 times x, just 3x. Then 3 times negative 2. Positive times a negative is a negative, which gives us negative 6. Right, on the third line is what we do to combine what's on the left. So the second line reads 2x plus 10 minus 7, right? 10 and negative 7, or 10 and minus 7, are like terms, right? Neither of them have a variable. They are both just numbers. So we can combine them to get positive 3. right? And everything else just carries down. On the fourth line is us combining our like term variables, our like terms that include variables. So what we did in this case is subtracted 3x from both the left and the right sides. So when we subtract 3x on the right, that gives us 3x minus 6 minus 3x. On the left, it gives us 2x plus 3 minus 3x. We can now combine, because we have two terms with x's in them, we can combine 2x and negative 3x to give us negative x underneath that. And then the positive 3 just stays down because it doesn't have a like term in this case. On the right-hand side, though, 3x and negative 3x equals 0x. That was the goal, right? We wanted to get one side with x's and the other side with just numbers. So negative 6 is just brought down. All right. Now we want to continue getting x by itself now that it's on the left. So we subtract 3 from both sides. So 3 minus 3 is 0, which leaves us with just negative x underneath this line. But on the right, negative 6 minus 3 gives us negative 9. Right. Even though x does not have any other terms next to it that are apparent to us, it still has a negative 1. It's still not alone. So we have to divide by negative 1 because there's an imaginary 1 coefficient being multiplied by the x. So to undo the multiplication, we divide by negative 1 on both sides. Always do it on both sides. And on the right, we are given negative 9 divided by negative 1. And a negative divided by a negative is a positive. So x equals 9 in this case. And you always want to plug this number back in to your original equation for that variable to make sure that it's correct. Alrighty, so John's height in inches, h, is twice that of his nephew's c minus 20. Which of the following algebraic expressions best represents the statement above? Right, so we are trying to write out an equation that represents how to solve when we are given actual numbers for at least one of the variables, right? So John's height in inches is represented by the variable h. So we know we have to have an h, and we also know we have to have a c, which is his nephew's height. John's height is twice his nephew's, all right? So we know that 2 times c minus 20 is equal to John's height, which is h. So in this equation, B would be our answer. John's height, h, is equal to 2 times his nephew's height, which is c, 2 times c minus 20. So in going about these, I always think, what are we trying to find and what variable needs to be set equal to the rest of the expression versus what variables go together. So in this case, the 2 times c minus 20 goes together because that is going to be used to solve for John's height. Ready? Next is the FOIL method. This stands for first, outer, inner, last, right? When multiplying two variables added or subtracted with another two variables added or subtracted, you add like terms. So example, 2 plus 2 equals 4, 2x plus 2x equals 4x, 2y plus 2y equals 4y. However, 2y plus 2x is not allowed because they are not like terms. And we'll get to this more on the right. So on the right picture, we have two sets of parentheses. We have a plus b times c plus d, right? To expand this out, we need to use the FOIL method. So first, we multiply the first terms together in both the sets of parentheses, which would be a times c. We bring that down in red, so it's just a times c, ac. Then the outside variables, we multiply a times d, so that gives us ad, and that's added to the first ac, so ac plus ad is what we have so far. Then the inside terms we multiply together, B times C, which is added at the bottom. So that so far gives us AC plus AD plus BC. Then the last terms are multiplied, B times D, which gives us plus BD at the end, right? And you'll notice that none of these terms are like terms now. AC plus AD plus BC plus BD, none of those have two of the exact same letters in the same place, right? So we can't further add these variables and terms together. So that would be the answer for this in terms of variables. However, you will be given this in terms of actual numbers, and you probably will have like terms. So make sure you know how to add like terms and make sure you know how to recognize what are not like terms so that you know when to stop combining. Next is inequalities. We need to know how to work with these. So if you divide by a negative, the alligator mouth flips. We'll talk more about this on the right picture. However, let's just go over first what the different symbols mean. So in the left picture, we have kind of like what looks like maybe Pac-Man's mouth, or I like to think of it as an alligator, where it's smaller on the left and it gets bigger as you go right. That means less than. If that symbol is flipped, where it's bigger on the left and smaller on the right, that means greater than, right? Whatever number is on the left is greater than what's on the right. Then, to the right of those two symbols is less than or equal to. It's the same way, it's the same orientation as the first symbol, the less than symbol, but it has a line underneath it, which represents or equal to. Same thing for the next one. That symbol is the same as the greater than symbol. However, it means greater than or equal to because there's a line underneath it. Now, the last symbol, it looks like an equal sign with a line through it, right? Which is exactly what it is. That means not equals to. Alrighty? So now on the right-hand side, we actually see an inequality that needs to be solved for that variable. So we need to solve negative 2x plus 6 is greater than, that symbol's greater than, 8, right? So first, to get x alone, we need to subtract 6 from both sides. When we subtract 6 on the left-hand side, it goes away. Positive 6 minus 6 is 0. So it just leaves us with negative 2x is greater than. Then on the right, we have 8 minus 6, which simplifies to 2. So the third line is negative 2x is greater than 2, right? So all we did there is subtract the 6 from both sides. However, now we still have a negative 2 being multiplied by x, so x is not alone yet. So the opposite of multiplication is division, so we need to divide both sides by negative 2. And when we do that on the left, the negative 2 goes away. And when we do it on the right, 2 divided by negative 2, positive divided by negative is a negative, and that gives us negative 1. However, our answer is not x is greater than negative 1. We divided by a negative here, so we have to flip the sign. We have to flip the alligator mouth. So our final answer is x is less than negative 1. All values less than negative 1 are possible answers for this equation, all right? X is not equal to negative 1. Our possible answer choices could be negative 2, negative 3, negative 1 million, right? Those are all less than negative 1. Ready? Next, we're just going to talk about some graphs, how to read them, how to use them. Ready? So graphs, we need to know how to interpret graphs and decide on which one to use for a particular data set. Visualizing data based on what the data is trying to represent is very good to help us know the trend of the data, or maybe we need to use it to solve for an unknown number, maybe make predictions, that sort of thing. Alrighty? So to choose a graph, you must think about what data you have. We'll talk about this more on the right-hand side. But the x-axis is known as the independent variable, and the y-axis houses the dependent variable, right? So on the right-hand side picture here, we have a graph that has temperature in degrees Celsius and sales on the left. So on our x-axis, the horizontal going from left to right, is our temperature. Temperature in degrees Celsius is our independent variable, right? And sales is on the y-axis going from bottom to top. That is our sales, all right, in dollars. So a proper title for this graph could be temperature in degrees Celsius affecting sales, or the effect of temperature on sales. All right. And I'm not sure what these sales are for. However, this is just a generic graph. All right. So as you can see, our first data point, our leftmost blue dot here, when our temperature was approximately 12 degrees Celsius, we had approximately $200 in sales, right? And our last data point, when we had about 25 degrees Celsius, our sales was a little bit over $600, right? And as you can see, this kind of looks like a linear line going from left to right, and it is increasing. So these are all things that you can gather from this graph, right? We know that as temperature increases, sales also increase. That is a prediction that we can make based on this graph. And it's also linear, so just a straight line. So the trend line for this graph, if we were to plot a trend line, it would be a linear line. Ready? Now, bar graphs, they are used for categorical data showing how much is within a single category, and it allows comparison of that amount to other amounts in other categories, right? So for the picture that we're given, different kinds of nuts is our title for this graph. So on the bottom, our x-axis, we have the kind of nut, almonds, cashews, walnuts, or peanuts, represented by different colors. And then on the left-hand side, we have number of students. I'm assuming this is representing the number of students that voted for their favorite kind of nut, or maybe number of students who eat those kinds of nuts, that sort of thing. So first we have almonds, all right? So that looks like a little less than 5 students that voted for almonds. However, we want to make it a whole number because we can't have like 4.9 students. That'd be a little scary, right? So we'll just say 5 students who voted for almonds or who like almonds. For cashews, we have 8 students that like those. Walnuts, we have 3 students that like those. And peanuts, we have 10. So we can just follow the bar up. For example, on peanuts, we can follow it up and it's almost on that black line. We trace it back over to the left. And so that's how we know it's 10 students. Right. Next is scatter plots. You'll notice that this is very similar to the first graph that we went over, which the first was also a scatter plot. So we'll go over those more in depth now. So scatter plots relate 2 variables to possibly show a correlation between them. The closer the data is and the more linear it appears, the more correlated the 2 variables are. However, correlation does not imply causation. Just because 2 variables occur at the same time doesn't imply they have a causal relationship. All right? So if we had a graph that showed a linear trend and our independent variable was number of ice cream cones sold, right? And our dependent variable was happiness, amount of happiness on a scale of 1 to 10, right? Those could be related, right? They could correlate in a way because it could show a linear trend. However, just because ice cream sales were up, just because people ate ice cream, does not mean that that's what made them happy, right? They could have gotten sick or other things, right? It doesn't mean that the ice cream caused their happiness. Okay? So scatter plots also show the relationship between X and Y. As X increases, Y increases or decreases, or as X decreases, Y increases or decreases, right? It's just dependent upon the graph. So in this case, on the right-hand side, our title of our graph is weight and height of children, okay? So we have our height on the bottom, which is our independent variable, and our weight on the left, going from bottom to top. That is our dependent variable. It's dependent upon the height of the child. All right. However, that doesn't imply causation, but as we can see, because it is a linear trend, there is correlation between the two variables, right? So we can look at the various data points, right? They're not all exactly on the line, and they probably are never going to be unless it is an exact linear line. We can just see the general trend increasing. So in this case, the relationship between X and Y is as X increases, as height of a child increases, their weight increases as well. Whether that is, causing each other or not, they are still correlated. Ready? Next is pie graphs. So pie graphs are used for categorical data, just like bar graphs, but they show the composition or parts of a whole. This is expressed in percent equaling to 100 or just numbers equaling the total amount. So on the right-hand side, we have a title of our graph, which is recommended diet. And we have a circle, looks like a pie, right? That's why it's called a pie graph. So we have different colors representing different parts of a diet. So first is fruit, which is in blue. The recommended portion of our diet that should be in fruit is 30%. Then protein is in green. The recommended percent of our diet for protein is 23%, followed by vegetables, which is 18%, dairy, 15, grains, 9%, and any other foods or any other parts of our diet is 5%. All right. And as you'll notice, all of these percentages add up to 100%. So all of the smaller parts add up to our bigger part, add up to our whole diet, add up to 100% of our diet. Right? So if you have any questions, you might ask them below, but I hope this was very helpful for you all. Some tips that I have for test taking strategies is just pace yourself properly. Don't spend too much time on any one question, even though you will get through other questions pretty quick. You might get through some questions really quickly, others might take you a long time. So make sure that you prepare for those longer questions by not spending too much time. However, also don't rush. You do want to take your time, just not overly use it. But good luck on your test. I hope you all do very well. Hope you all have a wonderful rest of your day.